Thank you, Debbie, and thank you very much for the invite to talk today. As Debbie said, I am the BRE lecturer in fire safety engineering, so Debbie has to put up with seeing me occasionally when I come down to say hello and share what we've been doing. As Debbie said, this piece of research was funded by the Engineering Physical Sciences Research Council immediately following the events at Grenfell. And what I wanted to do was share a little bit of the work that we've been doing. And I also wanted to explain a little bit about the sort of principles behind why we're doing the work and what the real reasons are. So we're all familiar with the events that happened on the 14th of June, and while the current interest in external flame spread is very much driven by this event, actually what's been happening since then is continuing to raise lots and lots of very fundamental questions. And so I don't want to talk about what happened at Grenfell. There's obviously a public inquiry, police investigation, all these things ongoing around that. But what I want to do instead is look a little bit about what has happened since. So as a researcher, it's always a little bit strange when you find yourself reading the BBC News website and you have genuine opinions and views on the specifics of what's being talked about. But one of the things that I sort of noticed over the course of the last years, there's been a lot of debate, there's been a lot of discussion, and this was something that I pulled out. This was on Question Time actually. It was Dominic Raab was talking to Diane Abbott. And he asked Diane Abbott, this was in the context of calling for a ban on certain materials, can you define combustible cladding for me right now in a way that is clear? It's a technical issue. And actually, Dominic Raab is really right on that. And I think what I wanted to do in the context of the research that we're doing is sort of think about the motivations for why this research is needed and what we can then use it for going forward. So this was a quote from Adrian Dobson. I've been listening to the Grenfell Tower podcast. I'm sure many of you have. And Adrian Dobson is a member of REBA. And they were talking about this idea of this cladding and should we ban different types of combustible cladding. And Adrian Dobson said, this is where it gets very technical, echoing the ideas of the minister at the time. And he sort of then went on to outline the position that REBA were taking in relation to combustible cladding. And he said A1 is fairly simple, it means non-combustible. And he says A2 has subcategories. So there's a category, for example, A2S1D1. So a material that combusts will produce smoke, and it will produce burning droplets that will then spread the fire. So that was what he said. And actually, Octavian had some of those classifications up just a moment ago. And then he went on to say that in our view, we need to move away from this oxymoron, this concept of limited combustibility. Let's keep it simple and let's have non-combustible. And so what I wanted to do, really to sort of show maybe why we need this research and why we need this understanding, is unpack that just a little bit. And so the thing that REBA are talking about there is the classification for the reaction to fire. And so what they have there is the first part of that is the material classification. That's A2 in this case. Then you have a smoke classification, which is something to do with the amount of smoke that material produces. And then you have a droplet classification. So that's the amount of droplets, burning droplets that a material might produce. And there's these different things, and it starts to look quite complicated as a build-up. Now, in fact, it's worth saying that this is what it actually says in the approved document. It's not quite as REBA had it, but nevertheless, there's a series of classifications around here, and so there's this call. I suppose it is a call. It's a call to have particular type of material A1 as opposed to A2 S3 D2 because it's seen as being more complex. Let's keep things simple. And then we go and we ask the question, well, why is that? What is going on behind the scenes here with these things, these different classifications that give us these different values? And this is what I went and got from the European standard. So this is the difference between those two classifications. And so we have A1 up here at the top, we have A2 down here, and this just tells you the different tests you need to do in order to get your product to a certain classification. And what you'll notice is that A2 has got an extra test in there. It's got a test, it's got a corner test, an SBI test. And so the reason why A2 has got those additional categories added onto it is because actually there's an additional test that's conducted on that material. And so I suppose it's just to illustrate that it may seem simple, we may look at something and think we understand it, but actually what's going on behind the scenes there is potentially a little bit more complex, and we need to take a great deal of care before we sort of start demanding things and asking things to make sure that what we're doing has got the appropriate technical background. But nevertheless, there's this distinction between A1 and A2, and it's essentially in this thing called the heats of combustion. So if we look at the difference in the heats of combustion, so the heat of combustion is the amount of energy that a material can release when it's burned. So the number of megajoules per kilogram of energy. So we have the A2 material here, which has got an allowable heat of combustion of 3 megajoules. And then we have the A1 material here, which has got an allowable heat of combustion of 2 megajoules. And so, again, you can see there's a difference there between these materials. But then if we compare that to other materials, so the other materials that we might use as a reference, we can see actually these materials all the way down here compared to something like polyethylene or timber or butane, that's a much higher heat of combustion. So again, I suppose I just put that out there to illustrate the importance of understanding the really digging behind what is presented in a standard, to be able to actually understand what it means, and then to be able to act rationally on the basis of that. The other thing I suppose I wanted to say is that these classifications are just that. They don't actually necessarily tell us anything about the real performance of a product, how it's actually going to behave in a fire. They're just a classification. They're used for ranking things. And so, I can accord a classification to each of these individuals standing behind the writing there. I can class them A to N, something over there. But what does that really tell me about their height, for example? Imagine some of these ones are going to grow a little bit, and their height is going to change, but I've already classified them. So just because we have a classification doesn't mean we can infer a particular level of performance. It's just a classification, and that's what it is. And so we just need to bear that in mind. So that was the kind of the context in which we've been undertaking this research, where there's an enormous amount of discussion going on, but there's also a lot of detail and background that really actually is sitting behind all of this. The other thing I suppose that's worth saying is, and we had Ken Knight here earlier, I think he's had to head off now, but is the building safety program. So this is a program that was set up in the wake of Grenfell, not to look at Grenfell itself, but to look at other buildings that might be affected. And they do monthly releases of data, so this is the latest set of data. So there's currently, I think, 466 buildings that they've identified with cladding that's unlikely to meet the building regulations. And so, and there's a whole data summary, you can go and look at this, pull it out yourself. So there's a big question, not necessarily on the new buildings, and that's the argument that's currently taking place, but the existing buildings that have already been built, that have got all sorts of disparate types of cladding system built up on them, that are maybe less extreme than those that might have been conducted as part of the DCLG tests that were conducted last summer, but nevertheless don't meet the building regulations. What do we do with these buildings? I mean, I keep on reading the press, and there's people, there's leaseholders who are subject, everyone, to £40,000 worth of renovation work. Is that appropriate? Is that not appropriate? These are the kind of questions that we really need to get a handle on to be able to act in an appropriate way. And then the other thing that I wanted to just draw your attention to, and as a research project, this has been a very interesting one to work on because things are changing so quickly, was this letter that was sent out by the MHCLG just a couple of weeks ago, 10th of September, and really that was clarifying exactly which parts of the approved document what they meant, and this was the paragraph that I pulled out because it's talking about the BS 8414 test, which we've just heard Octavian sort of making reference to, and it's in saying very specifically that if people are going to be using a result from a BS 8414 test, they need to make sure that test results must be relevant and appropriate for the proposed external wall construction. And of course, that was always the case, but just, I suppose, reiterating that fact. And so, again, thinking about the motivation for this, this is a BS8414. This is down in the burn hole, a photo that I pinched from the internet. And so if we have what is, obviously a large fire, and then we have the results of a test. So this is a system before and after. Again, these were these are actually pinched again from the internet. And we can see what a system looks like. This one's actually been deconstructed a little bit. Is how can we be sure that this system, or any system that is built, is actually going to be relevant and appropriate to the system that was tested against an 8414 test? That's the fundamental question that's raised by this letter. And so I suppose, really my answer to that question is we need to be able to join the dots in terms of what is happening in a particular testing scenario, given the products and assemblies that are involved, and what is happening on a building, and how are those the same, and how are those different. So what we need is the ability to join the dots up between all of these different factors to be able to understand, is this relevant, appropriate, or not? And that's where I suppose this research starts to come in. So again, one of the things I've heard a lot over the course of the last year, I suppose, is people talking about fire, but they don't often get very technical, and if they do, sometimes they get their facts a little bit wrong. So it's worth just thinking about what we mean by fire spread, because that is ultimately the issue here. And we have two types of fire spread when we're looking at a wall. We've got opposed flow fire spread, which is the downward fire spread on this diagram, and then we have concurrent flow fire spread, which is the upward fire spread. And those two types of fire spread are fundamentally different. One of them is governed by a very local condition taking place down here about how quickly energy is being transferred against the updraft, if you like, and the other is being driven by the preheating and the length of this flame as it's heating the material above it. And that is a fundamental difference in behavior. So if we go and look at some of the tests, now this is not actually a standard test, this is the lift test that was developed by Jim Quintieri, but is a test for lateral ignition and flame spread. And what that test does is it exposes a panel or a material to a heat flux, and that heat flux decays, and you measure how quickly the flame spreads from one end to the other. But this is a test for lateral flame spread, which for the purposes of this discussion is essentially the same as downward flame spread. It's against the direction of flow rather than being underneath the flame itself. And so really what we need to be able to do is understand, we want to know about the lateral flame spread. That's where a lot of classification testing comes from. But we also need to be able to understand this idea of vertical flame spread, upward flame spread. And what are the things that are controlling that? And this takes us to the kind of systems that we have been seeing a lot of recently. Some very complex systems, build-ups of lots of different pieces of geometry, and I've simplified this down to the kind of essence of what the kind of a common cladding system might look like. So you have some kind of existing structure, you overlay that with insulation, then you have a gap, an air gap to allow ventilation, and then you have the rain screen cladding sitting in front of this. And of course, this is what all of a lot of the debate has been about, and the different materials that are being used in these kinds of systems. And so, if we want to start understanding the performance of these systems, we have to start asking ourselves lots of questions about what are the things that might impact upon the way that system may or may not behave. And so, questions that we could ask, we could say, well, what is the influence of the width of the cavity? If I was to conduct a BS8414 test, and I had a 50 millimeter cavity, and then I want to change to a 60 millimeter cavity, is that important? Does it matter? Do I need to go and retest, or is my result fit for purpose as is? The location of the gaps between different panel assemblies, does that matter? Does it have an influence? The thickness of the different materials. if I change my insulation thickness, if I change my rain screen thickness, is that going to have an impact? The types of materials I'm using, so actually what they're made of, is that going to have an impact? The combination of materials, how I put them together, is that going to have an impact? The fixing of materials, so the actual, the mechanical way these systems are put together, does that have any influence on the overall fire performance? And of course, Octavian was talking about cavity barriers just a moment ago. The location of the cavity barriers and the way they're put together, does that have an impact on performance? And so there's a whole range of the complexity of these systems that we need to have an understanding of if we're going to be able to start really making sure that we have relevant and appropriate application of any test results. And so this is where our research came in. And so we've been doing a lot of work in the lab. So we have a lab up at Edinburgh. We have a furniture calorimeter. We can do medium-scale experimentation, and we've been doing that for a number of years on these kinds of materials. But really what we wanted to see is what is going to happen at the slightly larger scale. And so what I wanted to do now is just share with you a little bit of the work that we've been doing, and so you can see the kinds of things that we're pulling out from this research. So we did the work in 2 phases, one phase in January, which was very warm in the burn hall, and one in May and June, as a team of 8 people came down for this research. And what we did is we used this BS8414 rig as the basis for the start of our experimental build-up. And we all learned how to drive a scissor lift, so I'm now a qualified scissor lift driver if you require any assistance. And what we did is we took a modular system. So we created a framing system that we could then mount lots of different combinations of material to, and we mounted this onto the wall. So what you can see here is the first of the frames going up. We did have a time lapse of this actually, but it's a little bit embarrassing because you can just see us forgetting our tools and having to go up on the scissor lift the whole time. So I decided not to play it. And so we can start to mount this system on the wall. David Farrington was delighted that we drilled a series of very large holes in his wall so we could fit our instrumentation through. And then this is the instrumentation going down the back of the rig behind the wall. So we had around a little bit more than 200 sensors across the whole array. And then this is looking at it from the side. So what you can see is each of the modules here going up the height of the wall, and you can see there's an absolute tangle of cables and tubes sitting behind the wall, which are feeding our equipment. And so this is the kind of scenario that we have. So we have the masonry wall, we have a fire that's out of sequence, we have the instrumentation zone sitting here, which is what you can see in there. We've then got a vermiculite board. So this thing you can see here is vermiculite. So that's pretty much an inert material, often used for kind of lining furnaces and the like. Then what we've done is we've overlaid a sheet of PMMA onto that. Those of you who've done fire labs in the past will know PMMA very well. It's plexiglass and is a very well-studied material in terms of its properties, in terms of how it burns. So what we wanted to do is we wanted to take something we really understood how it burnt, but put it in a situation that was quite extreme. And so then what we did is we ignite it at the very bottom, and we used the smallest ignition source that we could get away with and still get an effective ignition. So we just had a strip of soaked ceramic paper that was soaked in heptane. So a very small ignition source. So what I'm going to play you now is a video. So this system, it's worth saying that this does not look like a cladding system. I think it's fair to say. PMMA and onto the vermiculite board does not look like a cladding system. What it gives us is a baseline. A lot of the experimental research that's previously been conducted in this area is really looking at the fire spread on a single surface. And so what we wanted to do is the kind of thing that people normally do at kind of 1 meter scale or 300 millimeter scale, but do it over 7 meters in order that we could get a baseline for behavior of a very, very simple system, which is what we did. So hopefully we'll play a video. So what you can see here, this is actually the other rig, because this was the one in January that we did where we occupied the other wall, but it was exactly the same system, just inverted. And I'm pleased to say there were no funny symmetry effects on this wall. We measured that, so we managed to we're very happy that we had a symmetric experiment. And so we've got 7 meters of PMMA. Now, what you can see here is each one of those is an individual panel that's just 1 meter high, and you can see there's a little black thing there. That's actually the a pressure probe that's measuring velocity of the gas directly in front of the panel. So what you can see down here, 2 minutes in, 4 minutes in, we've got little flames at the bottom, and it's starting to get a little bit bigger over here. What we have here is the observed flame length. So this is just eyeballing this from this video, and you can see the growth rate. So now we're kind of reaching up to about 1 meter, 1 and a bit meters, I guess. And what you can notice here is you're starting to get an accelerating curve. So by this time you've got ignition of almost a whole height, but not quite. And then you've just got this little bit at the top here that's then igniting towards the very end there. What you can see at the bottom, we only have a 6 millimeter thick piece of PMMA. So at the bottom, it's burning out, and by 12 minutes 38, you've actually had burnout across the entire, almost the entire height, except at the edge where it was restrained to keep it all in place. And then at that point, got a little bit nervous for the roof of the burn hole, so we put it out. But what you can see here is exactly what I suppose you would expect to see based on the fundamental theory of the flame spread, in that we have a self-accelerating fire. So it's an exponential growth rate. So that's our kind of baseline case. No one's ever done anything, as far as I'm aware, quite on that scale before, in terms of the size of that experiment. But as I say, it's only the baseline. Really what we now then want to understand is what are the processes that are controlling the fire spread in something that looks a little bit more like you would have in a real building. So this is the build-up that we then created. So it's a very similar idea, masonry wall, our instrumentation zone. It's worth saying that's all our instrumentation sort of going out the back of the wall. Actually, a lot of it was coming through to actually take the readings within the samples themselves. And then what we did is we used a couple of different insulation materials. We used a PIR, which is 100 mil thick with no foil. I'll explain that in a second. And we used a mineral wool material. Now, the reason why we used no foil, and I was having this conversation with someone in one of the breaks, is that when we start to get into this territory, we've got a very complex system here. We've got very complex processes governing the flame spread. What we want to be able to do is simplify as much of the things as we can. So we already have an idealized setup, as we've sort of discussed, but also what we don't want to be testing specific products. We want them to be as simple as possible. So a lot of the products that we have, particularly installations, they have a foil on them, and that introduces a great deal of complexity in terms of the way pyrolysis gas exits the material, and it creates a lot of uncertainty. We wanted to have a material we really understood how it was going to behave. So we have what's here is just a material, not a product. So it's a material of PIR 100 millimeters thick, and the same for the mineral wool as well. And so then what we did is we ignited it, the PMMA in exactly the same way. So note that we ignited the PMMA, not the insulation material. So it's exactly the same ignition source sitting below the PMMA, but we ignited it on both sides this time because the PMMA is sitting out in the cavity. Things that we're interested in is the flame spread, is the flow within the cavity, it's the flow outside of the cavity. We're looking at heat flux, we're looking at the gas temperatures, all of those things we're measuring the whole time we go along. And again, this is because what we want to do is we want to quantify the processes that are taking place. This is my disclaimer. Everything we used was a material, not a product, so no letters, please. And then I'm going to play you the video. So these are side by side. So one on the left you've already seen. That's one I just played you. That's no cavity straight up. And then this is the stone wool insulation in there. And then this is one with the PIR. So these are going to be replaced by the videos. And so you can see the same ignition. So this is PIR, this is Stonewall, and this is just without just the PMMA direct. Now what you can see, or you can start to observe just the differences that we have here in terms of the flame spread. So this one is a little bit slower to begin with. This one is looking fairly similar at this stage, but suddenly at about 1 minute 30 it starts to accelerate a little bit. This one is obviously already well light in the vertical flame spread going upwards. What you can also see is the streamlines here from behind the plexiglass, because the plexiglass is transparent, so you're looking into the cavity. This one you can see on the outside at the bottom here, you've got fire on the outside, and then you've got fire on the inside. So by this time we're nearly at the top of this rig over here, and we're getting down to this one over here, and then by this point the PMMA is starting to melt and fall away. And you can see as the PMMA falls away, the flaming is not really sustained on the PIR sitting behind that, because there's no heat source there to heat it. At that point, we realized that our instrumentation was getting burnt at the back, so we put that out. It was just a pool fire on the floor anyway. And then this one is a lot of the PMMA has already landed on the floor, and so essentially what we have here is just burning at the edge of the samples, and we realized we actually lost our entire instrumentation at the back of the panel in that one. And then here we have, without the cavity, is a video that you've seen before. So I suppose coming up for the end of my talk, as always in research, we get some answers, we have lots of questions. What is the relative contribution of different materials here? When does the cavity matter, when does it not? Which processes are governing the fire spread, and how can these be mitigated? And so all of the instrumentation that's used in experiments is going to allow us to start quantifying those things, to actually start understanding the role of different processes and different materials within the fire spread in these kind of assemblies. And it's my fundamental belief that it's only by addressing these kind of questions that we can ensure that we're doing this relevant and appropriate interpretation of test results. And it's really only by addressing these questions that we're going to be able to come to rational solutions for these buildings that are stuck somewhere in between, where nobody quite knows what to do with them. We're going to be able to provide some rational engineering answers to these. So with that, I just want to acknowledge the team. As you can imagine, doing something on this scale requires a lot of people. So Rory Haddon, who's Eric, Chris, Mikhail, Chris Bateman, George and Vasilis, who is up here today. So thank you to them, and thank you to BRE for putting us up with us on campus for a month while it took to do the experimentation. Thank you.
Well, thank you very much for that talk. That concludes the speaking for today. I'd like to ask if anybody has any questions for either Octavian or Angus. Please, if you want to wave your hands, and we'll get a microphone to you. Okay, we've got one down the front here, please, and then one in here. In fact, they're both quite near the front, so whoever gets the microphone first.
Thank you. It's John Allen at LABC. The question's for Octavian. The work you've done on the cavity barriers, we're looking then into prevention. Did you do anything with the ventilated cavities, or was it just with the insulation that's stuck on the wall?
No, it was just with the insulation. So yeah, all of the work was focused on EPS systems, so ETIC systems actually. The cavity barriers that are involved in ventilated facade, they are way more complex, and the process is more complex. So yeah, I think this is another bit of research that we have to look at.
And that was all research that was done in Romania,
yes,
of course,
yeah.
So it wasn't done here. Yeah. Okay, yeah, please.
Good afternoon. Question for Angus, Nick Jenkins from Boothmere. With the assemblies that you considered, it's very interesting to look at those. Was there or is there plan to also compare one of those assemblies with the addition of cavity barriers, which are of course, a requirement of regulations. Whether they've actually been installed is another question, as we're aware. And would it have not been more relevant to actually use materials rather than, or products rather than materials, because that's perhaps telling us more about the real world than an experiment of products that aren't generally used in facades?
Yeah, so I mean, I think in terms of the use of the products, the challenge we have is, you know, we have a set of products that are themselves an assembly of different materials, and they behave in a very complex way. We know that from small-scale experimentation. And then we have a very complex assembly in which those are assembled. If we then try and understand the processes that are driving the flame spread in an arrangement like that, it's very hard to pin down which are the governing processes. You know, is it the heat transfer? Is it the flow? Is it the chemical reactions? What's taking place? And so your question is kind of right in terms of, you know, relevance to that result to the real world is a valid question. But in terms of being able to understand the processes, unless we know what those processes are, we can't really start to draw any generalized conclusions. Now, if we simplify what you have as products down to very simple materials, relatively simple materials, then what we are able to do is understand the small-scale stuff, and that gives us a real good shot at understanding the processes that are driving the large-scale experimentation. Then, of course, once you understand what the processes are, then you can start to think about how those processes might interact with different products. But if we took a set of building products and put them on the assembly, the complexity would be such that it would be very difficult to learn anything at all beyond showing the videos. Whereas what we've got is gigabytes and gigabytes of data that we're currently crunching through in terms of the performance of each of those bits of the system that we can quantify. There were two parts to your question. What was the first part?
The use of cavity barriers.
Yeah.
One of those assemblies.
Yeah, so I mean, what cavity barriers are doing there is they're introducing a brake, so they're stopping flow. And so one of the things that we considered as part of this project was, should we try introducing something to mitigate the impact of the flame spread? But the direction we ended up going was to conduct a slightly broader experimental program across different parameters. On the basis, if we understood the processes, if we understood, for example, that flow is dominating here, then we would know that introducing a brake would be an effective way of stopping that flow. If we realized it was the heat transfer that was dominating, then it might be another mitigation measure might be more effective. So again, by understanding the process, you start to be able to draw some rational conclusions about what is an appropriate mitigation for a given system.
Other questions? Yeah, we have Tom behind you, Gemma.
Hi, I'm Tom Roach from FM Global. So, listening to your presentation, this is to Angus, you seem to be reinforcing the fact that we really don't understand these systems and how they burn today. And if that's the case, and then how much longer do you have to go before you think you're going to understand it? So when do you finish? Is that in 12 months, 18 months, 24 months, just to sort of bound this project?
So I mean, in terms of understanding the complexity of all of these products, that is a very difficult challenge. I think that you're right. All of the historical work that's been conducted around flame spread is on a single surface. Then there's a whole series of work that is introducing an additional surface in a cavity. And then what we have here is a problem where we have different materials, either side of a cavity, and then actually not even materials, it's a product, either side of a cavity. And so if you think about the additional layers of complexity that we're having here, they're very substantial. Now, in terms of being able to characterize which processes are driving it, that is something that's potentially more easy to do. You might not be able to model all of the bits, but in terms of understanding what's important, that's actually something that these sort of tests are set up and designed to do. And that's where we can start to make those decisions. Now, I'm not going to commit to a timeline to deliver you an answer on that one, but I mean, I think your question's fair.
I mean,
So it's fair, but just in terms of timeline, how long does your project actually run? How long
So
are
we
you funded
finished the
for?
experimental phase, and we're hoping to publish by the end of the year, and then by probably a couple of papers next year as well.
Thank you.
So, I mean, Tom, you'll be aware that BSI at the moment is writing an extended application document for BS 8414, because at the moment, basically, what you test is all that the test result is valid for. And obviously one of the questions is, well, if you vary the cavity depth on a system, is that okay? And the answer is, well, nobody's looked at it systematically, so nobody really knows. So the sort of work that they're doing at Edinburgh should hopefully start to answer some of these questions to allow some of that to take place. Otherwise, people are ending up just having to test the system and not being able to vary any of these types of parameters.
I mean,
I think that's a very good point to make to a lot of people in terms of understanding of these systems and understanding variations of these systems and whether we've truly understood that. And you know, taking a line from Hollywood, good luck.
Yeah, I mean, it's worth saying that what David said is in a way the motivation for us undertaking this project. As soon as the events of last summer unfolded, we realised, well, we'd been kind of wanting to work in this area and get funding before, but what we realised is that these were the kind of questions that we're going to need answers to, and we're going to need answers pretty soon, and so that was why we've sort of undertaken the research.
Just a simple question. Steve Grayson, InterScience. I'm not sure if I didn't see your slide correctly, but did you use different thicknesses of insulation between the stone wall and the PIR? I thought I saw that the PIR was 100 millimeters, and the stone wall was 25.
That is correct. Yep.
Why did you do that if you were comparing materials?
So what we wanted to do was characterise the thermal boundary conditions, and so in a way what was important was we knew what was going on more than we were, so we can either control everything or know very precisely what the performance, or what the conditions were. So yes, the insulation was different, but what we did is we characterised the heat flux going in, and we had thermocouples within each of those materials to allow us to understand what the heat transfer was taking place. So we can quantify the losses out of the system associated to the different configurations, and on that basis we can then understand what is the contribution of not having as thick a set of insulation.
That's what you find out after the experiment. I mean, why didn't you use 25 millimeters of PIR and 100 millimeters of stone wall?
We could have done. It was an arbitrary decision.
I was just thinking about the presentation of that. It looks as if the fire development inside that system was more extreme inside the PIR, whereas if you'd have had the balance the other way around, maybe it wouldn't have been. On the ITV news, that's the way it would come across.
Yes, so I mean...
and is that the reality?
Well, I think that's, in a way, those are the kind of questions we need to answer, aren't they? And so one of the parts of this project that we're working on is to do the same set of experimentation over a much wider range of parameters at lab scale, in order that we can validate what we're seeing at the large scale. So, things like, insulation thickness, all of these are parameters that we need to know. But at the moment, we don't, I suppose, have an answer to that question.
I mean, maybe I'm sure your physics is much better than mine, but I would have started off with them at the same thickness. But
okay. Can I suppose if what we really want to do is characterise the boundary conditions that we have in a system, because thickness of the insulation doesn't necessarily tell you anything about what its ultimate thermal performance is going to be. So it's what we really need to do is measure it and understand it, rather than control it.
Any other questions? No? Okay, so thank you very much. If you could please just join with me and thank all of the presenters for today.